title. This is actually two short talks stitched together, and so necessarily the treatment in each one will be a little bit superficial, and I hope you'll bear with me and when I skip over a few of the details. These are two somewhat separate talks, and they come with two sets of collaborators. Because we've already begun this session of the MRI workshop on thermodynamics and vertically stratified disks. I hope you've all realized that you moved away from the workshop on dynamo and Prandtl numbers. That's with Omer and Shigenobu. And then the second part on global simulations is with Scott Noble, John Hawley, and Chris Beckwith. And just as Omer emphasized, the real heavy lifting in the first project was done by Shigenobu, and Scott Noble was the principal actor in the second part. Okay, so this is now the final installment in this discussion of, my email is running. Maybe I should turn that off. Let's see how many spams I get per unit hour. Anyway, I'll just quickly remind you that we're interested in this subject because when disks are centered on relativistic objects, neutron stars or black holes, particularly neutron stars with relatively weak magnetic fields, so the magnetosphere comes in close to the surface, the inner rings of the disks in the bright disks, the ones that are most interesting in many respects, are generically expected to be dominated by radiation pressure. Technically, that criterion depends on the ratio of stress to pressure, but it depends on that ratio only as the 2/21st power, so it really hardly matters. It could vary almost any way you like with radius, have almost any value, and that criterion would not change a whole lot. So this really is an important problem for those accretion disks around neutron stars and black holes that we observe the most. I'll just remind you here, as Shigenobu explained, this is exactly the same argument he presented of the fact that the alpha model does truly predict thermal instability. And as you saw, because we find, in fact, thermal stability, the question is, where did it go wrong? And at first glance, that's rather mysterious. This is another presentation of the same data Shigenobu showed you already. The dissipation rate does more or less rise with pressure. It's not quite linear. The mean slope there is more like 0.8 rather than 1. There is some curvature, but it definitely does go up with increasing pressure. And so you might ask, why don't our simulations exhibit that instability? Well, to understand that, I want to go back to the origins of the alpha model itself. And if you go back in the beginning, the reasoning was dimensional analysis. Stress and pressure both have units of force per unit area, and since both stress and pressure appear in this problem, Shakur and Sinyaev quite reasonably argued that they should be related and have some quantitative relation that's sort of order unity. But that doesn't necessarily tell you which one is controlling the other, or whether both are controlled by some other agent, or whether that ratio, albeit order unity, is constant or varies or what. The problem is that I think basically through an historical accident, right from the start, it's always been easier for us to estimate pressure than to estimate stress. And that was especially true in the 30 years ago when we hadn't a clue what was actually making the stress. But we have a pretty good idea what makes pressure. And that, I think, led to a mental habit of thinking that pressure ultimately controls stress. And some of that, I think, was sort of accidentally reinforced by a result that came out of the MRI approach, in which we knew that as the field strength grows, the fastest growing wavelengths grow, and when they become too big to fit in the thickness of the disk, then the instability goes away, and that corresponds more or less to b squared being order of the pressure. However, if you think a little harder about what's really going on here, in fact, it's much more likely to run the other way. That is to say that first comes the magnetic part and only later comes the pressure. Where the pressure comes from is ultimately dissipation of magnetic energy and the turbulence that it drives. So the real sense of causal direction comes first from the agencies that take free energy of orbital shear and put that into magnetic field, and then all the complicated internal dynamics of magnetic turbulence that transforms large-scale fluctuations into smaller-scale fluctuations, and all the wonderful microphysics that somehow puts that into heat. But only then does the energy become available for pressure. This is direct evidence that that's the right point of view. Shiganova briefly mentioned that the magnetic fluctuations precede the radiation, and here it is. There's a cross-correlation from one of the simulations with P radiation much larger than P gas, and the sign convention on the lag is that negative corresponds to magnetic fluctuations leading radiation fluctuations. Here is the zero lag point. You can see that there is definitely a correlation between radiation energy and magnetic energy at zero lag, but the correlation is better with lags between about -15 and -5 orbits. That is, with the magnetic energy fluctuations leading the radiation by 5 to 15 orbits. The thermal time in the simulation, on average, was, I believe, something like 13 orbits. So this is roughly one thermal time of lead. And that corresponds very well with this qualitative sense that first the magnetic energy fluctuates, and then after about a thermal time, the pressure equilibrates to that. Now, I'd like to transform those qualitative words into the simplest possible quantitative model. And the point here is to operate on the simplest, most global level, partly to get the big picture overview of what's really controlling things, partly also to skirt all possible technical questions about the details of dissipation. Admittedly, these simulations have uncontrolled dissipation rates. It's all grid scale numerics. It's not controlled microphysics in any fashion. But what I want to show you is that because we can reproduce the primary aspects of the thermal properties of this simulation with such a simple global model, I don't think its conclusions are going to be very sensitive to those details. There may be quantitative adjustments, but I think the big picture is pretty robust. And what's being shown here is, let's see, is there a light pointer, one of these guys? This looks like it. Yeah, there we go. Okay. Simplest possible relationship here. All these energies are box integrated, and the picture is that the magnetic energy is driven by some characteristic rate, and it may be sensitive, that driving may be sensitive to the radiation energy, parameterized by this power n, but there are intrinsic fluctuations that just have to do with the way the turbulence operates. Okay? So that's a random function. When I solve these equations, I'm going to realize this random function simply by taking a Fourier power spectrum that's drawn from the simulations, or the magnetic fluctuations, and choosing random phases. Then the magnetic energy is dissipated at some characteristic rate. That dissipation goes into the radiation, and then radiation leaks out by cooling. Of course, you really want to non-dimensionalize these. And when you do so, the time scale here is actually in units of this dissipation time. There's the power n in the driving rate response to the radiation energy. And there's also power s here. I'm letting the ratio of cooling time to dissipation time scale with the radiation energy to the s power, on the thought that when the radiation energy increases, you expect the disk to thicken. The cooling time is basically h over c times the optical depth. because the surface density doesn't change on these time scales, the optical depth is fixed, but if the thickness changes, that might change the cooling time. Okay. And then you can see that the radiation energy changes more slowly than the magnetic energy, basically by that ratio of the equilibrium magnetic energy to radiation energy. So the simplest, most, as I said, free of detail, whether for good or bad, picture that you could draw of that qualitative picture in which magnetic fluctuations drive the pressure. What comes out of that is, with remarkably little effort, is a thermal history that looks an awful lot like simulations. This is the same data that Shigenobu showed you. The only difference is that I'm plotting it on a log scale instead of a linear, and that allows me to make the magnetic energy and the gas energy sort of at the real levels, not multiplied by 10. Over here is that toy model with these parameters n and s both set to 0. That is, there is no sensitivity in the driving of the magnetic energy to the radiation energy. It's completely independent of the radiation energy. And just for simplicity, I set the cooling time dependence to be null. You can see that these fluctuations are rather similar. I also did a little parameter fitting. There's an amplitude to r of t that I chose arbitrarily to make these amplitudes match up. But I don't think that's a significant issue. Still, you get the same kind of fluctuations, and it, of course, is clearly thermally stable.
So just to clarify, what are you putting in?
Okay, what I'm putting in are...
Specifically this, you said you put in the power spectrum of something?
Oh, I'm putting in the random function. Maybe I'll go back to the equations. Here. Okay. This random function has an amplitude of 0.3 in a certain sense that I chose just to make the fluctuations a reasonable size. It has a... Pardon? I'll get to that, I think. Elliot asked exactly what I chose, and that's one of the numbers I chose. But, okay, let me finish this description. The R of t has a power spectrum that's taken from the sort of simplified version of the power spectrum of magnetic energy fluctuations in the simulation. Okay? Which was roughly f to the minus 1 at low frequencies, f to the minus 3 above 1 over the thermal time.
So getting the magnetic fluctuations to look roughly right is a...
Yeah, that's right. That's right. The key thing is that, as you'll see in a moment, the evident stability and a follow-up result, which is one slide along. Okay? The last thing that's put in is this ratio here, and I chose that to be 0.01 because it was the simplest small number I could choose. Mm-hmm. Okay. Okay. There is some thought, some people think that the saturation level of the magnetic field is sensitive to the pressure. And I wanted to allow for that. In the particular realization that I showed on the next slide, I removed that sensitivity, but the results that I get are not in any quality, I should say, are extremely insensitive to that value of n. I've tried other values, and it doesn't make much difference, and you'll see why, the very simple reason, in a moment. Okay? Yeah?
In the previous slide, on both curves, the ratio of magnetic energy and radiation energy seems to be of order 100.
Yeah.
Is that this parameter that you chose?
Okay. Here, that's the simulation. That's real. Here, it's the parameter I chose.
So that it's the same ratio?
This ratio is a little bit bigger. Maybe it's 0.02 or 0.03, but it's, like that. Okay. Okay, so after the fact, although there is no explicit relation between pumping the magnetic field and the pressure, you get a correlation after the fact. Okay. There's, magnetic energy. In this case, I actually did a least squares fit in the logs. I think the best fit power law was 1.01. It's very nearly linear. But all that tells you is that this is a thermal balance on average situation. there's no thermal runaway, so it's net thermal balance. And if you go back to those equations, in thermal balance, the long time average of the left-hand side is 0. So that means the magnetic energy must be just proportional to radiation to the 1 minus S, and in this case, S was 0. In other words, you indeed find a correlation of magnetic energy on radiation energy, but it has nothing to do with the pressure driving the magnetic stress level. All it comes from is thermal balance, because the radiation energy derives from dissipation of the magnetic. Okay. And in fact, because the slope of this correlation just depends on ER to the 1 minus S, it's telling you about how the cooling time changes with radiation energy, that's the slope is. It's not telling you anything about that driving term. In other words, there is no requirement from these data for the saturation level of the magnetic field to have anything to do with the pressure. Doesn't rule it out either, but just masked, because the primary relationship in the end is driven by thermal balance and not by any explicit connection between the saturation level of the magnetic field and the pressure. Okay. Which means that I think we need to think a little harder about the question, what really does control the saturation level of the stress? I think there's, as I said before, a very strong sort of tradition of the null hypothesis being that it has something to do with the pressure. And in fact, we may be better off thinking about this as ultimately the surface density and orbital frequency are really the independent parameters in terms of thermodynamics and stress. And certainly they are in these simulations. They act jointly to control the magnetic field intensity and the pressure. And perhaps there is some back reaction of the pressure on the magnetic field. But in the end, it's really these two that control the field intensity and the pressure jointly. And here's where dependence on Prandtl number, et cetera, may also come in, because that depends on density and temperature and so on. But I think that may be the more appropriate way to view the saturation problem, rather than just fix the pressure and find out what the stress does in response. And
I'm sorry, so Red's supposed to be answering the question raised in the green?
It's more a sort of change of point of view than a very clear answer. It's where do you want to start thinking about this? I'll readily admit that I cannot draw you a well-defined path from these two variables to the equilibrium field strength.
Could you not have done a similar thing instead of focusing on radiative equilibrium, but focusing on conservation of momentum?
Conservation of momentum?
Yeah, I mean, and say that what's responsible for the stress, accretion stress, is the mechanical pressure, the pressure of the system, rather than
But it's clearly not. I mean, it's not a simple relation. That's what I showed you, for example, with that cross correlation.
You showed that one comes from the other, but I mean, how specific? What is the specific reason that you're saying one comes from the other?
What I'm saying is that in a time sense, magnetic fluctuations precede pressure fluctuations.
But isn't the flow oscillating?
Not in any regular way. If it were a regular oscillation, you wouldn't have any net sense of lag. Yeah. You'd have a double peak.
I still don't quite see what you're saying here. I mean, what time scales are we talking about? I mean,
Okay, we're talking on time scales that are short compared to the inflow time, so that you can fix the surface density, but long compared to thermal and hydrostatic equilibrium.
okay, so those time scales,
One at a time, please.
those time scales, both sigma and omega, are fixed, whereas in the previous view graphs you're talking about.
Sigma and omega also were fixed. Sigma and omega were also fixed throughout this.
Right, okay, but you've been talking about fluctuations in magnetic
Yes?
So, sigma and omega are not relevant to saturation or to controlling the.
Oh, well, there is a net level that ultimately is determined, right? And if you, okay, I better move on to the second half.
Minutes more, so you
Okay.
decide when you want to silence this guy.
Okay, I think I will move on to the second half.
Wait, but
Elliot, yeah. There will be time for a question.
go back to the punchline about thermal stability. It's stable. It's stable.
Yeah, there's no disagreement there.
The
Okay.
diagonal elements of the stress tensor don't control the off-diagonal elements of the stress tensor.
Okay. In fact, they don't even control all the diagonal elements. Right? Okay, so yesterday Fausto told you about the kinds of functions that your grandmother taught you. Well, you may have a similar attitude toward the radiative efficiency numbers for accretion onto a black hole. I mean, these were worked out so long ago, you may feel that you learned them somewhere around third grade. But I want to return to where they came from. Once again, this is sort of going back to the beginning. And that's the Novikov-Thorne model, whose principal elements were, first of all, everything's done in proper full general relativity. You expect nothing less from those authors. They took the simplest, non-trivial picture of an accretion disk around a black hole, time steady, axisymmetric, geometrically thin, so it made sense to vertically integrate all properties, and applied the equations of energy and angular momentum conservation. Now, both of these require a boundary condition because they're flows. In the case of the energy, it's ultimately closed by saying that the dissipation, the heat, is carried off to infinity by radiation. And in fact, they, in order to make this all self-consistent, they assumed that any heat was promptly and locally radiated and then carried off to infinity. In the case of angular momentum, the angular momentum flows through the material, and you could conserve it for any value of the flux. Choosing the actual value of the angular momentum flux is equivalent to choosing a stress boundary condition at the innermost stable circular orbit. One determines the other. And they chose, for some simplicity and based on hydrodynamic plausibility arguments, that it should go to zero there. Now, as a consequence, flow inside the ISCO is in free fall, so matter arriving at the black hole has the energy and angular momentum it had at the ISCO. And that means that the radiative efficiency is nothing less than the binding energy at the ISCO, because the matter arrives at the horizon with rest mass energy minus that binding energy. And presumably, the binding energy was carried off in photons.
Wouldn't you agree that it seems like the boundary condition of the ISCO, because of the equations you are assuming are scaling the problem, in physical reality, just let matter at the outside of this is going to migrate inwards, and why we would care about ways at the ISCO? The same matter like being
it determines the problem. That's what you need to close the equations. And as you'll see, because that's equivalent to supposing that the flow is free fall inside the ISCO, it fixes the binding energy of matter arriving at the horizon. And remember, the deepest part of the potential is where most of the energy is released, so it matters. Okay. Now, that assumption of the inner boundary condition was problematic right from the start. Thorne republished the Novikov-Thorne model in a pair of after articles the year after the SOSFE conference, which it first appeared, and this fascinating quote appears in one of those two papers. And in 1974, it was perfectly reasonable for Thorne to say, I don't want to worry about magnetic fields. Magnetic fields, like patriotism, are the last refuge of scoundrels. But we've spent the last 2.5 days thinking very hard about what magnetic fields do in disks, because we now know, thanks. Well, yes. Some of us have spent the last 17 years. And Steve and John taught us that they're, in fact, of the essence. So we better take them seriously and examine what consequences they have for that guessed inner boundary condition. Here are data from 2 simulations done with John Hawley, Jean-Pierre de Villiers, and Shigenobu Hirose. This one, Schwarzschild metric. This one, spin parameter of 0.9. And what's plotted is the vertically integrated fluid frame magnetic stress in bound material. At a particular instant in those simulations, that's the solid curve in both cases. The dotted curve is the Novikov-Thorne model prediction for the average accretion rate in the relevant simulation. And what you can see is that the magnetic stress goes straight through the ISCO without any obvious effect at all. Okay, and in fact, here's an interesting little side point here. The stress is, of course, angular momentum flux. It has to roll over and die just outside the horizon when it's a Schwarzschild hole because a non-rotating black hole has no angular momentum to give. When it's around a rotating black hole, there's no such restriction. And in fact, we find consistently that the stress just continues right smoothly down to the horizon.
But you have to multiply this by some complicated function of radius to get the angular momentum flux.
Okay, this is also local fluid frame, so that's, you have to be careful about in which frame. I presented it in this fashion because basically that's the way the Novikov-Thorne model works, so it permits a direct comparison. Okay, now it's been difficult to get at the consequences for radiative efficiency hitherto because, well, the Hawley-de Villiers code is based on an internal energy equation, and so doesn't conserve energy. It's not very good for thermodynamics. It's great for stresses, but not for the energy. The HARM code, developed by Charles Gammey and John McKinney, does solve a total energy equation, and it's intrinsically flux conservative, but in its original form, it was only axisymmetric. So there's a little bit of technology transfer when Scott Noble moved from working with Charles to working with me, and in which he brought HARM 2D and spent a year extending it to 3D, which he did successfully. And in order to study the radiative efficiency, we made a further modification to it. First of all, it's the right kind of code, I stressed, to follow the energy because it does solve the total energy equation. In its native form, this equation has 0 on the right-hand side. Stress energy is conserved. But if we want to find dissipation, losses, we need to put them in some fashion. And the device that we took was to put in a non-zero right-hand side in the form of an optically thin toy model cooling function, which was jiggered so as to reproduce nearly the essential assumption of Novikov-Thorne in this regard, which is to say the prompt local radiation of all dissipated heat. Minus 2 minutes? Yeah, okay, this is, I'll speed up, thank you. Okay, but I need to say what, because this is, okay. This is the simplest form, so it's a scalar cooling function, and then that's equivalent to having the radiation isotropic in the fluid frame, so it really is the net losses of radiation momentum energy are proportional to the Fourier velocity. And you can't radiate all the energy or else the thing would collapse to 0 and you can't simulate it. But by choosing a scale height that was small, we could radiate nearly all. And this is the form of the radiation function that we chose. So it has a target thickness h. And notice it's at a characteristic rate, which we just chose to be the local orbital frequency. Okay, maybe I'll skip the animation view of the time. The one thing you do want to see here is that this was spin 0.9 and target thickness 0.1, which it actually hewed to quite closely, except in the inner disk where it actually got thinner. It got down to maybe 0.04 near the ISCO. And the total duration of the simulation was some 15,000 m, g equals c equals 1.
This shows you radii in the horizontal direction.
These are m. Okay, so half the Schwarzschild radius. Yeah. Okay, and that's an animation. If you're interested, I'll show you. Okay, so results. Here is the surface brightness in the fluid frame averaged over this 2,000 m stretch. The reason for only doing 2,000 m is that these data are so fresh, and the next slide requires, many hours per 2,000 m of computing. And this was done last Friday afternoon at about 4 o'clock. So we just snipped out a sample. In any case, this is the surface brightness in the fluid frame, vertically integrated. And as you can see, matched against the Novikov-Thorne model in large radius, as the conservation laws insist, they sit right on top of each other, but it just continues right in here smoothly near the ISCO where the boundary condition makes a difference. The same thing in terms of radiation reaching infinity, and this is the last slide, is plotted here. This is the part that took a little more computing. And this is now luminosity per coordinate radius, per radial coordinate. Okay. And this includes the effects of photons lost by capture to the black hole. And again, there is an interesting supplement to what you'd expect just from Novikov-Thorne. Quantitatively, it's going to be roughly, I think, in the 15 to 20% range. That number isn't quite pinned down. As I said, we haven't looked at the entire simulation. We need to tune up a little bit numerically there. But it's going to be something in that range. And there's an interesting amount of heat that's actually advected into the black hole, about 2 or 3% in rest mass units, because that cooling rate is only order the orbital frequency, and whereas that's fast compared to inflow in the main body of the disk, it's only comparable to the inflow rate in the plunging region. Depending on the real radiation physics, that could be either an underestimate or an overestimate. But it looks like there is an interesting effect at that level. Okay. And I think you can read that and ask questions now.
I have a comment, Julian.
Mm-hmm.
My student, Rebecca Shafi, has done precisely the same experiment. Pretty much the same cooling too,
Mm-hmm.
with H around 0.1, using HARM, same code, but a different version. And we looked not at the luminosity, but we looked at what the angular momentum is doing.
Mm-hmm.
And Novikov-Thorne says that you come down to the ISCO, and then the specific angular momentum is constant because there's nothing further happening inside. The MHD simulation, of course, has got stresses inside the ISCO and stuff happens inside the ISCO. But you can still ask, what is the specific angular momentum of whatever goes into the black hole? And how different is it from Novikov and Thorne? It's reduced by only 3% in this experiment. So, you know, almost like it's irrelevant.
Oh, but you need to look not just at the angular momentum of the matter, but also the angular momentum carried in the fields.
That's what we're looking at.
That's significant.
No, this is exactly what we're looking at. It's 3% different from Novikov and Thorne.
Wait, the total angular momentum.
Yep. Yep.
That,
This is what leads us to believe that all this so-called action inside the ISCO is really not doing much.
have you integrated your cooling function?
No, that's a different story because we don't believe the cooling function can be used for. Anyway, this is technical stuff. I think Jeremy.
I wanted to come back
Yeah.
to the first red and green slide. The simulated, it may be true that dimensional analysis is not sufficient.
Mm-hmm.
That's certainly true.
Mm-hmm.
On the other hand, any physical explanation, since our units of measure are arbitrary, ought to be consistent with dimensional analysis. You can't make, you can't make something with units of pressure out of sigma and omega alone. So, what are you suggesting? I don't want to defend the idea of pressure control stress. I never really believed that.
Mm-hmm.
But what are you exactly suggesting? I just don't understand that slide.
What I'm really suggesting is a sort of change in viewpoint, that it may be that what you really need to look at is more of these sort of connections between those two and the radiative losses and so on. I have not fully thought through that dimensional analysis point. Yeah.
There are enough, I think, parameters in the problem to give you all the dimensions.
There are plenty more parameters.
Yeah.
No, but there is a
But
vertical
that may be,
If there was an idea.
well,
There is a vertical
well, Ramesh may be right.
There's
But,
vertical
as well.
yeah,
Radiation
yeah, yeah, yeah.
But that's the source of, that's the source of the energy. There's the physics.
Guys, one question, yeah.
I can have a question. First, thank you. It was very interesting and insightful. You talked, I think, on both sides of it. But I have a question about the second part.
Mm-hmm.
Outside of the ISCO, the material accretes relatively slowly, so it's optically thick. So if there's a flash of optically thick, it radiates as optically thick. Inside of the ISCO, is it optically thick or optically thin? Because it's free falling, I guess the surface density goes
Okay.
down.
That actually depends on parameters. I should explain that in these simulations, there is no sort of definite unit of density in the accreting material. It's just an arbitrary code number that can be scaled. And if you then say, aha, I want this to represent an accretion problem with such and such accretion rate and such central mass, then you can get an absolute scale of density and surface density. And for reasonable numbers, then it's sort of marginal. So that, that's a maybe.
So the region, the budget region may be optically thick or optically thin.
It's going to depend on the details. Yeah.
Right, I think, okay,
So
very quickly, yeah.
very quickly, how precisely do you calculate this lag from the first half of your talk? The lag between magnetic energy and
As precisely as that cross correlation shows it. That's the best we can do.
which is an average over what and what?
Okay, we have,
So magnetic
okay, we sample these things every hundredth of an orbit for 600 orbits. And, that gives, 60,000 samples.
and this is integrated over the whole box.
These are box integrated quantities.
Okay. Let's start.